Hi, I'm Jimmy from Princeton. In this video, I'll be presenting our work, Learning Pneumatic Non-Prehensile Manipulation with a Mobile Blower. This is joint work with collaborators from Princeton, Google, and Columbia. In robotics, we typically use contact-based primitives such as grasping or pushing to manipulate objects in the environment. However, in this work, we find that blowing can be a more effective alternative, especially when moving small scattered objects. Compared to contact-based primitives, blowing has several key advantages. It can move objects that are far away, greatly increasing the effective reach range of the robot. It can move objects at speeds much greater than a robot's own speed. And it can manipulate objects of different shapes and materials without complicated grasp planning. Given these advantages, we study the use of blowing in a cleanup task, where the goal is to move small scattered objects into a target location. We attach an air blower to our mobile robot and train it for the task using model-free deep reinforcement learning. Training a mobile manipulation policy to complete this blowing task presents several challenges. First, the objects can exhibit complex aerodynamics, so it can be difficult to accurately predict the effects of blowing actions. This means that the policy must learn to continually adapt to unexpected changes in a closed-loop manner. Second, completing the task requires both long-range planning and fine-grained control. The robot needs to place itself at strategic locations before turning the blower on, which involves long-range planning. Then, once the blower is turned on, it may need to execute multiple fine-grained blowing actions to move a pile of objects. To address these challenges, we use a multi-frequency version of spatial action maps. Spatial action maps is a framework for learning mobile manipulation. In spatial action maps, a fully convolutional queue network is trained using deep queue learning to take in overhead image observations and output a dense queue value map from which the best action is selected and executed. A key benefit of this approach is that image observations and queue value maps are pixel-wise aligned. This allows us to learn vision-based policies with actions that are directly anchored on visual features of the scene, such as piles of objects. To handle the unique challenges of mobile manipulation with a blower, we use a multi-frequency version of spatial action maps. In such a setup, we have 2 or more frequency levels, each with its own subpolicy. The low level executes at a higher frequency and takes k steps for every high-level step. In this example, k equals 2, so after each high-level step, the low-level subpolicy will execute for the next 2 steps. This formulation allows us to learn a policy that can handle both long-range planning and fine-grained closed-loop control. All policies are trained in simulation environments built with PyBullet. We simulate the blowing primitive by shooting invisible wind particles out of the blower. We find that even with such a simplistic model of airflow, the policies learned in the simulation can directly generalize to the real world. Now let's look at some results. Here we show a comparison between pushing and blowing, where each robot is running a trained policy using one of the 2 primitives. We can see that blowing is much more effective at moving the scattered objects. Quantitatively, blowing is roughly twice as efficient as pushing in this environment. In the presence of obstacles, the difference is even greater. The blower can easily move objects around the obstacles using airflow, whereas the pusher needs to carefully push objects along each individual obstacle. We also perform the same comparison in the real world, where we again see that blowing is much more effective than pushing. For all real-world experiments, we train policies in simulation only and run them directly on real hardware without any fine-tuning. We observed that the aerodynamics of real-world blowing are much more complex than the simple airflow model used in simulation. In spite of this, we find that our simulation train policies generalize well to real-world objects. Now let's take a look at how well our policies can generalize to objects that were not seen during training. We first look at whether the policies can handle heterogeneous objects. Specifically, we test with objects of mixed sizes as well as objects of mixed shapes. We find that our policies are able to generalize to these heterogeneous objects with no fine-tuning, even though they were only trained using homogeneous spheres. We also test on novel objects in the real-world environment, running our policies directly on the real robot without fine-tuning with the new objects. Here we show the robot working with objects that are larger than what it was trained with. Since the larger objects are heavier, they do not move as far when blown, so they require more actions to be moved the same distance. However, we find that our policy handles this well by reacting in a closed-loop manner and executing more blowing actions to compensate. As a final test, we look at whether a policy can handle loose maple leaves. Compared to the spherical objects used in training, these leaves exhibit much more complex dynamics due to their irregular shape and unpredictable movements. However, we observe that the robot can still complete the task effectively, again without any fine-tuning of the policy. For further details, please check out our webpage.